Have you ever walked into a room and forgotten why you went there? Or felt a sudden chill for no reason, as if someone were watching you? We usually explain such moments by saying that our brain is playing tricks on us due to fatigue or other reasons. But what if that's not the case? Personally, I no longer believe that, because when we finally mapped the boundaries of the universe, we saw that it is not a solid universe, but that there are real damages in it. It's more like a dent or a scratch where something from outside has physically hit our reality, and energy is leaking out of our universe from this damage. The equations show that our universe is not floating in a vacuum, it is drowning in a crowded ocean. We are being pushed and pulled by massive objects that are right next to us, just a few centimeters away, in a dimension we cannot see. I did a little research, and it changed my whole view of the world. We're not just going to talk about distant stars. We're going to look at evidence that the wall between these realities is cracking, and what actually happens to your body when it finally breaks down. Let's start with the universe. It is not as isolated and safe as we thought it was, at least physically. To understand this, let's turn to physics. The entire standard model of physics, the rules that dictate how your atoms hold together, relies on one specific assumption: that the Big Bang was a perfect, symmetrical explosion. This concept is called isotropy. It means that if you look at the universe in any direction, strictly speaking, the temperature and the distribution of matter should be exactly the same. Imagine pouring a drop of milk into a cup of coffee and stirring it perfectly. Eventually, the mixture becomes uniform. There are no lumps left. That is what the early universe should look like. A smooth, even soup of radiation with no special directions and no scars. But in 2013, the European Space Agency launched the Planck telescope to test this assumption, and the map it sent back destroyed the idea of a perfect universe. Instead of a smooth, uniform surface, the thermal map of our cosmos revealed a massive, unexplained violation of symmetry. The data showed that the southern half of the sky is significantly colder and structurally different from the northern half. This isn't just a random fluctuation of numbers on a screen. This is a physical deformity in the shape of space-time itself. The map reveals that the microwave background, the oldest light in existence, is lopsided. Think about what this means for you. Sitting right here. You are living inside a structure that we thought was a perfect sphere, but the data proves that the structure is bent. Inside that cold hemisphere, the telescope found something even more disturbing. A concentrated bruise on the fabric of reality known as the cold spot. In a closed system where energy is conserved, a spot this cold and this large is statistically impossible. It shouldn't exist. The laws of thermodynamics say that heat flows from hot to cold until everything is equal. The fact that this cold spot has refused to heal for 13.8 billion years suggests that something is keeping it open. It implies that the universe is not an isolated bubble expanding into nothing, but a physical object that has been struck by something else. So, if the laws of physics state that our world must be uniform, where did this massive dent come from? Who or what hit our universe hard enough to leave a scar that has lasted since the beginning of time? To identify the source of that impact, astronomers focused their instruments directly on the center of the anomaly in the constellation Eridanus. They needed to find the massive object responsible for the temperature drop. But instead of a supercluster or a dense gas cloud, the data revealed a complete absence of material. They discovered the Eridanus Supervoid. This is a continuous sphere of emptiness that spans 1.8 billion light-years across. To put that scale into perspective, it is the largest single structure ever identified in the history of astronomy. But unlike the Great Wall of Galaxies or superclusters, this structure is defined entirely by what is not there. According to the standard Cosmological Principle, the rule that says matter should be spread out evenly like butter on bread, a region of space this size should be packed with energy. The math predicts that we should see roughly 10,000 galaxies inside that volume. We should see gas clouds, dark matter, and the light of trillions of stars. But when we look into the Eridanus Supervoid, The lights are simply out. The matter isn't just dim, it is missing. Think about walking through a dense, noisy city and suddenly stepping into a block where the buildings, the people, and the sound have simply vanished, leaving only cold pavement. That is what this void is. It contains 30% less matter than the rest of the universe. It is a cold, dark desert in the middle of a lush rainforest. And because there is no matter to radiate heat, it creates the deep freeze we saw on the Planck map. But here is the physical problem with a hole that size. Gravity takes time to move matter. To clear out a space of 1.8 billion light years, to push 10,000 galaxies out of the way naturally, would take longer than the current age of the universe. Gravity is too weak to have dug this hole by itself in just 13.8 billion years. So, we are looking at a sector of space where thousands of galaxies have seemingly been scooped out of existence. But if something powerful enough to wipe clean a billion light years of space is active out there, how do we know we are safe sitting right here? The immediate question is whether a hole that size could just be a random fluctuation in the gas. Maybe the galaxies just didn't form there by chance. To test that, physicists calculated the statistical odds of a void that large appearing in a standard universe. When researchers crunched the numbers on the cold spot, they calculated the probability of a structure this large and this empty forming randomly in the standard model. The answer was less than 1.85%. In statistical physics, that number is a red alert. It effectively rounds down to 0. It means that under the laws of gravity and thermodynamics as we know them, the cold spot should not be there. Think about the room you are sitting in. The air molecules are bouncing around randomly. It is theoretically possible that by sheer chance, all the air could suddenly rush into one corner of the room, leaving you in a vacuum. But the probability is so low that you bet your life it won't happen. The cold spot is that vacuum. If the universe were a closed system, a sealed box where nothing gets in and nothing gets out, energy cannot just disappear. It has to go somewhere. The fact that this region is missing so much heat and matter implies that the system is not closed. The dice didn't just roll a double six. Someone reached onto the table and turned the dice over. This statistical failure forces us to consider the forbidden conclusion. The anomaly wasn't formed by internal luck. It was formed by external pressure. The void is not a random clearing in the forest, it is a footprint. So, the math says that a hole of this magnitude is effectively impossible without outside interference. But if something from outside already broke into our world once to create this void, how do we know the next breach isn't happening right now? This idea of an external force isn't just an attempt to explain the data after the fact. We know the model works because a theoretical physicist named Laura Mersini-Houghton actually predicted this specific hole 7 years before we had the telescope to see it. To understand why her work matters, you have to understand the problem with string theory. For decades, critics called it philosophical math, because it seemed impossible to test. The theory posits that our universe is made of tiny, vibrating strings in 10 or 11 dimensions. It suggests that there are roughly 10 to the power of 500 different ways to fold these dimensions, creating a vast landscape of possible universes. Most physicists thought this landscape was just a mathematical abstraction, a list of possibilities on a chalkboard. But in 2006, Mersini-Houghton published a series of papers proposing that this landscape is a physical place. She argued that our universe is just one bubble emerging from a high-energy background, like a bubble of steam rising in a pot of boiling water. And just like bubbles in a pot, universes crowd each other. They jostle for space. And inevitably, they collide. This wasn't just poetry. She ran the equations for what would happen if two of these cosmic bubbles bumped into each other in the early moments of their expansion. Her math predicted that the collision would unleash a massive shockwave of gravity that would push matter away from the point of impact. Based on this model, she made a specific, falsifiable prediction years before the data existed. She said, "If the multiverse is real, The upcoming Planck Satellite data will show a giant void, a cold spot, in the southern hemisphere of the sky. She even calculated the size. When the Planck data finally arrived in 2013, the scientific community was stunned. The cold spot was exactly where her equations said it would be. It was the right size, the right shape, and the right temperature. The probability of her guessing those coordinates by accident is statistically zero. This turned the cold spot from a random mystery into the first experimental evidence of the multiverse. We aren't just looking at a hole, we are looking at the verified crash site of two realities. So, the calculations proved the collision happened long before we ever saw the scar. But if the math isn't lying, and we really did crash into another universe, we have to ask the physical question. What actually happens to your matter, to your atoms, when they get hit by the gravity of a whole new world? Her equations don't just predict the location, they describe the mechanics of the event. According to this model, when two universes touch, they don't crash like solid objects, they interact through a massive gravitational transfer. Think about how gravity works. It is the force that pulls things together based on their mass. The Earth pulls you down. The Sun pulls the Earth. But gravity has a unique property. It is incredibly persistent. It reaches across vast distances. And according to the models of the multiverse, gravity is the one force that can leak across the boundary between universes. In the Mersini-Houghton model, when our bubble universe touched the neighboring bubble, they didn't just bounce off each other. For a cosmic moment, they interacted. The other universe had mass, huge amounts of it. And where there is mass, there is gravity. Imagine you're holding a vacuum cleaner nozzle against a sheet of fabric. The fabric is our universe. The vacuum is the gravity of the other universe. When the nozzle touches the fabric, it doesn't tear a hole. It pulls. It creates a bulge. It sucks everything loose towards that point of contact. In the early moments of the Big Bang, our universe was not made of solid stars and planets. It was a hot, dense soup of plasma. It was fluid. When the collision happened, the gravity of the neighboring universe acted like that vacuum. It grabbed onto the plasma in that specific region of the sky and pulled it hard. It dragged the gas, the dark matter, and the potential energy away from that spot, pulling it toward the boundary wall. It literally siphoned the building blocks of reality out of that sector. This explains why the Eridanus Supervoid is so empty. It isn't a random quiet spot. It is a crime scene. The 10,000 galaxies that should be there aren't missing because they didn't form. They are missing because the raw material needed to build them was stolen by a neighbor. We are looking at a region of space that was strip-mined by the gravity of a larger, heavier reality next door. So the evidence suggests that a massive alien gravity simply reached in and dragged an entire cluster of potential galaxies away from us. But if this force is strong enough to move the furniture of the universe itself, what creates the friction that stops it from pulling the rest of the house down? While Mersini-Houghton was predicting the cold spot, a team at University College London led by astrophysicist Stephen Feeney decided to take a completely different approach. They didn't just want to explain one scar, they wanted to see if the victim had other injuries. Feeney realized that human eyes are terrible at finding subtle patterns in chaos. We see faces in clouds where there are none, and we miss real structures in noise. So, in 2010, his team built a sophisticated computer algorithm designed to hunt for one specific shape in the cosmic microwave background. Rings. Why rings? Because physics is consistent. If our universe is a bubble floating in a multiverse, a collision with another bubble shouldn't just leave a shapeless bruise like the cold spot, it should leave a ripple. Think about throwing a stone into a perfectly still pond. The impact creates a concentric circle that expands outward. If the universe is a fluid-like plasma in its early stages, a collision with another membrane or bubble universe should send a circular shockwave of temperature variance rippling through the cosmos. Feeney's algorithms scanned the entire sky, looking for these faint circular echoes that no human could spot. and the computer found them. It didn't just find the cold spot, it identified 4 distinct circular patterns embedded in the radiation of the Big Bang. This discovery fundamentally changes the story of our existence. If you walk out to your car in the morning and find a single dent on the bumper, you might assume it was a freak accident. Maybe a stray shopping cart hit it. You can write it off as bad luck. But if you walk out and find dents on the hood, the doors, the roof, and the trunk, you stop thinking about luck. You realize that your car has been in a demolition derby. The presence of 4 separate impact rings implies that the collision wasn't a one-time event. It suggests that our universe is like a battered vehicle driving through a hailstorm of other realities. We haven't just been hit once, we are being buffeted. We are enduring a systemic bombardment. This paints a picture of the multiverse that is far more violent and crowded than we ever imagined. We are not floating in an empty void. We are navigating a dense, chaotic foam where universes are constantly jostling, merging, and bouncing off one another. The history of our world is written in the scars of these impacts. So, the data shows that these crashes are happening repeatedly, over and over again. But if you are in a car that keeps getting hit, eventually you realize you aren't just parked in a bad spot, you're driving into traffic. If we are constantly colliding with something, does that mean we are moving toward it? Before we can talk about the monster that is pulling us, we have to talk about the ground rules. To do physics on a galactic scale, you need a map. And every map needs a fixed point, a north, to orient yourself. In our universe, that north is not a star or a galaxy. It is the cosmic microwave background. The CMB is the afterglow of the Big Bang, a sea of photons that fills every inch of space. It is the absolute reference frame for the entire cosmos. If you are sitting still relative to the CMB, the temperature of the universe looks exactly the same in every direction. If you move, the light in front of you gets slightly bluer, hotter, and the light behind you gets slightly redder, colder. This is the Doppler effect. The same reason an ambulance siren changes pitch as it drives past you. This leads us to the single most important rule in astronomy, the Cosmological Principle. This principle states that on a large enough scale, the universe is isotropic and homogeneous. That means it looks the same everywhere. It implies that matter is distributed randomly, like gas in a box. There are no special directions. There are no privileged spots. There are no giant currents. According to the standard model of cosmology, known as lambda CDM, galaxies should move like bees in a swarm. They buzz around randomly, attracted to their nearest neighbors by gravity, but the swarm itself stays put. The average velocity of the universe should be 0. If you measure the movement of 1,000 galaxies, their random motions should cancel each other out. Some go left, some go right. The net result should be stillness. This isn't just a guess. It is the foundation of every equation we use to calculate the age and size of the universe. If this rule is wrong, our entire understanding of physics crumbles. But when we actually look at the data, the swarm isn't buzzing randomly. The data suggests that the cosmological principle is a lie. Instead of random chaos, we see order. We see a coherent flow. It is as if someone opened a window in the box and a draft is blowing through. The galaxies aren't just drifting, they are being steered. This violates the core assumption of isotropy. It suggests that space-time itself has a slope, a gradient that we can't see, but can definitely feel. Think about standing on a frozen lake. You assume the ice is flat, but if you put a marble down and it starts rolling faster and faster in one specific direction, you know your assumption is wrong. The ice is tilted. So, if the bedrock of physics says the universe should be flat and still, why do our instruments show that the floor is tilted? If the entire cosmos is sliding downhill, what is waiting for us at the bottom? To answer that, Alexander Kashlinsky needed a way to measure the absolute speed of distant clusters without being fooled by the expansion of the universe. You can't just look at the redshift of stars because that data is contaminated by the stretching of space. So his team used a completely different tool called the kinematic Sunyaev-Zeldovich effect. Instead of measuring light emitted by the galaxies, they measured how the electrons in those galaxies physically hit the photons of the background radiation. So, how did Alexander Kashlinsky and his team at NASA figure out that the galaxies weren't just expanding, but flowing? They stopped looking at the light from the stars and started looking at the shadows in the radiation. They used a phenomenon called the kinematic Sunyaev-Zeldovich effect, KSZ. This effect is subtle, but it is the only way to separate the expansion of the universe from the actual motion of the matter. Imagine the cosmic microwave background, CMB, as a rain of photons falling evenly from the beginning of time. Now, imagine a massive cluster of galaxies, a huge ball of hot gas and millions of stars, moving through that rain. When the CMB photons hit the hot gas, the electrons, inside that cluster, they scatter. They get a tiny energy boost. If the cluster is moving toward us, the photons get a specific blue kick. If it is moving away, they get a red drag. This change in energy has nothing to do with the expansion of the universe. It is a direct speedometer reading of the cluster itself. Kashlinsky didn't just measure 1 or 2 galaxies. He took the data for roughly 1,400 massive galaxy clusters scattered across the sky up to 3 billion light-years away. This is a sample size that covers a significant chunk of the observable universe, about 10% of everything we can see. According to the standard model, the random motions of 1,400 clusters should look like static. Some move left, some right, some fast, some slow. The average should be 0. But when Kashlinsky processed the KSZ signal, the average wasn't 0. The clusters were moving in lockstep. The data showed that these thousands of galaxies, separated by billions of miles, were all drifting in the exact same direction at a speed of nearly 1,000 kilometers per second. They were not behaving like gas molecules bouncing randomly in a box. They were behaving like a solid object. It was as if the entire local universe had been caught in a river current that we couldn't see. So, we aren't just looking at a few rogue stars. We are looking at 10% of the visible universe moving as a single, coherent body at the speed of a bullet. But if something is strong enough to grab a chunk of reality that big and drag it, are we just passengers on a sinking ship? So we have established that a massive chunk of the universe is flowing like a river. Naturally, the first question any physicist asks is, where is the drain? If we are moving, we must be moving towards something. Gravity requires a source. When astronomers plotted the trajectory of this flow, they found it was heading straight for a specific patch of sky located between the constellations of Centaurus and Hydra. This creates a massive problem for observation because that direction points directly through the zone of avoidance. This is the thick band of dust and stars in our own Milky Way galaxy that blocks our view of the deep universe behind it. We are essentially driving down a highway at 2 million miles per hour with a dirty windshield. But using radio telescopes that can punch through the dust, we found the first suspect. We called it the Great Attractor. This is a gravitational anomaly about 250 million light-years away. A massive concentration of galaxies, the Norma cluster, that is pulling on everything in our neighborhood. For years, we thought this was the answer. We thought we were just falling into a local pothole. But when we finally measured the mass of the Great Attractor, the math broke. It simply wasn't heavy enough. It is big, sure, but it isn't strong enough to drag 10% of the visible universe at 1,000 kilometers per second. It's like trying to move a freight train with a household magnet. So, we looked further, behind the Great Attractor, and we found a monster. We found the Shapley supercluster. This is the single largest concentration of galaxies in the nearby universe. It contains the mass of 10,000 Milky Ways packed into a relatively small volume. It is a gravitational titan. Scientists breathed a sigh of relief. Surely this was the engine driving the flow. But then they looked at the speedometer again. If the Shapley supercluster were the sole cause of our motion, then the galaxies closer to it should be moving faster, and the galaxies further away should be moving slower. That is how gravity works. It gets weaker with distance. But the data from Kashlinski's flow showed something impossible. The velocity vector was constant. Galaxies 1 billion light-years away were moving at roughly the same speed as galaxies 3 billion light-years away. The flow didn't care about distance. It didn't fade. This implies that the Shapley supercluster, despite its size, is just a pebble in the stream. It is being carried along with us. The force that is pulling us is not local. It is not falling off with distance because the source is so unimaginably massive and so incredibly distant that the gradient looks flat to us. We are not falling towards a star. We are falling towards a horizon. So, if the Great Attractor is too small and the Shapley supercluster is just another piece of debris in the current, what is left? If the gravity isn't getting weaker as we look further out, does that mean the source of the pull has infinite power? Or is the monster simply too big to fit inside our universe? When physicists run out of objects to blame inside the room, they have to start looking at the walls. We have weighed the Great Attractor. We have weighed the Shapley supercluster. We have summed up the mass of every visible galaxy, gas cloud, and dark matter halo in the direction of the flow. And the result is terrifyingly simple. The math does not add up. Even if you combine the gravitational pull of every single object we can see in that slice of the sky, it is not enough to accelerate a chunk of the universe to 1,000 kilometers per second. It accounts for maybe 20% of the speed. The other 80% is coming from a ghost. This forces us to confront the hard limit of our reality, the cosmic event horizon. Because the speed of light is finite, we can only see objects whose light has had enough time to reach us since the Big Bang. That gives us a bubble of visibility roughly 46 billion light-years in radius. Beyond that edge, the universe is dark to us. We cannot see what is there. But gravity doesn't care about light. Gravity is a curvature of space itself, and it can ripple across boundaries that photons cannot cross. Here is why this breaks the standard model. According to the theory of cosmic inflation, the universe should be much, much larger than what we can see. But crucially, inflation predicts that the unseen universe should look exactly like the seen universe. It should be uniform. If there is more stuff outside the bubble, it should be distributed evenly, pulling us in all directions with equal force. The net result should be zero. But the dark flow proves that the unobservable universe is not uniform. The fact that we are being yanked in one specific direction with such overwhelming force implies that there is a massive imbalance just beyond the edge of our map. There is a titanic structure, something far larger than any supercluster, larger perhaps than our entire observable bubble, sitting just over the horizon. It is tilting the floor of the entire cosmos. This suggests that our universe is not an infinite, uniform plane. It suggests we are finite, and right next to our edge, there is another massive object, possibly a neighboring brain in the multiverse, that is close enough to drag us down. Hook. So, if the source of this gravity is strictly outside our bubble of reality, it means we are being acted upon by an alien force we will never be able to see. But if we are already caught in its gravitational grip, is it pulling us towards a collision? Or are we simply orbiting a monster we cannot comprehend? In 2017, a team led by cosmologist Yehuda Hoffman at the Hebrew University of Jerusalem made a discovery that completed the map of our motion. For decades, we had been obsessed with the monsters in front of us, the Great Attractor and the Shapley supercluster. We assumed that because we were moving fast, the gravity in front of us must be immense. But when Hoffman looked at the velocity data again, he realized the math still didn't quite work. The pull from the front wasn't strong enough to explain our speed of 630 kilometers per second. Something was missing from the equation. He realized that we had been looking at only half the picture. Gravity is a game of tug-of-war. If you have a massive object on your right pulling you, you move right. But if you also have a massive object on your left pulling you, you stay still. The forces cancel out. Hoffman found that the region of space directly behind our Milky Way isn't just average, it is empty. He discovered a vast, localized void that is almost completely devoid of galaxies. In the dense map of the cosmos, this empty patch acts like a negative mass. Because there is so little matter there to pull on us, the gravitational tug-of-war is rigged. The Shapley supercluster pulls us forward, and the lack of gravity behind us effectively pushes us away. He named this region the Dipole Repeller. This discovery changed our understanding of the local universe from a static map to a dynamic engine. We are stuck in a massive cosmic current. On one side, we have the attractors, dense regions of superclusters sucking matter in. On the other side, we have the repellers, expanding voids pushing matter out. Think of it like a river flowing downhill. The voids are the high ground, shedding their matter. The superclusters are the low ground, the drains collecting everything. Our galaxy, the Milky Way, just happens to be caught in the steepest part of the slope. We are surfing a gravitational wave that spans hundreds of millions of light years. We are not drifting randomly, we are being expelled from the void and consumed by the cluster. So, we now know that this is not a random drift. It is a global flow of all matter, from the minus of the void to the plus of the attractor. But if we are trapped in a current between a push and a pull, is there any way to steer the ship, or are we just debris headed for the waterfall? If you accept that the universe is a river flowing from the dipole repeller to the Shapley attractor, the next logical question is, where does the river end? Rivers don't flow forever. They empty into oceans. And in astrophysics, an ocean is a region of infinite density. According to the standard model of the universe, the lambda-c DM model, the future is supposed to be lonely. Dark energy is pushing galaxies apart faster than light. Eventually, the Milky Way should be isolated, floating alone in a dark, expanding void. That is the heat death scenario. But the dark flow data contradicts this prediction for our specific region of space. If you take the velocity vectors of the thousands of galaxies measured by Kashlinski and extrapolate them forward in time, they don't drift apart, they converge. We are not heading toward isolation, we are heading toward a traffic jam of cosmic proportions. The gravity of the Great Attractor and the monsters behind it is overcoming the expansion of the universe locally. It is pulling the Milky Way, Andromeda, and thousands of other galaxies into a steadily tightening knot. This creates a scenario that physicists call a localized Big Crunch. While the rest of the universe might be expanding into cold nothingness, our sector is collapsing. We are falling into a gravitational funnel. As we get closer to the source of the flow, the density of matter will skyrocket. Galaxies will merge. Stars will be ripped from their orbits. The accumulation of mass in that one specific region of the sky will eventually create a gravitational well, so deep that it mimics the conditions of the singularity that started the Big Bang. Think about water circling a drain. At the edges, the water moves slowly, but as it gets closer to the center, it moves faster and clumps together. We are currently swirling around the edge, moving at 600 kilometers per second. But the physics of the flow suggests that we are spiraling inward. This implies that the dark flow is not just a movement through space, it is a movement toward a specific destiny. We are being collected. We are being compressed. But here is the unsettling part about drains. They usually lead somewhere else. If huge amounts of matter are being sucked out of the normal expansion and concentrated into a single point, physics suggests that point might be a breach. A singularity doesn't just crush matter, it punches a hole in space-time. So, we are being herded into a gravitational pen along with millions of other galaxies. But why is the universe trying to concentrate so much mass in one specific spot? And what happens to our reality when we finally reach the bottom of the funnel? In 1919, a virtually unknown mathematician named Theodore Kaluza sent a letter to Albert Einstein that changed physics forever. At the time, Einstein was famous for general relativity, which describes gravity as the curvature of space and time. But there was another force that nobody could connect to gravity: electromagnetism, light. They seemed like two different languages. Kaluza did something simple but radical. He took Einstein's equations of gravity, which work in our familiar 4 dimensions, 3 of space, 1 of time, and he just added a 5th dimension. He didn't know what it was, he just wrote +1 in the math. When he worked through the equations with this extra room to move, something magical happened. The extra components of the gravitational field didn't disappear, they transformed. They naturally automatically produced the exact equations for electromagnetism derived by James Clerk Maxwell decades earlier. This was the first successful unification theory in history. It proved that gravity and light are likely the same force, just vibrating in different dimensions. But this created a massive problem. If there is a 5th dimension, why can't we see it? Why can't we walk into it? In 1926, a physicist named Oscar Klein solved this riddle. He proposed that dimensions come in 2 types: extended and compactified. The 3 dimensions we know, up down, left right, forward back, are extended. They go on for billions of light years. But the 5th dimension is rolled up. Think of a garden hose lying on the grass. From an airplane, it looks like a 1-dimensional line. But if you are an ant crawling on the hose, you realize it has a 2nd dimension, circumference. You can walk around it. Klein argued that the 5th dimension is curled up into a tiny circle at every single point in space. It is smaller than an atom, too small for us to see or enter, but it is there. It is the hidden loop where gravity vibrates to become light. This is not science fiction. This mechanism, compactification, is the mathematical bedrock of almost all modern theoretical physics. Without it, the math of the universe simply breaks. So, the math proves that a 5th dimension isn't just somewhere else, it is here. It is curled up inside the atoms of your body and in the empty air in front of your face. But if space is folded up like a blanket, what could be hiding inside the folds? By the 1990s, physics was in a crisis. The unification dream that Kaluza started had fragmented into a nightmare. We had not 1, but 5 different versions of string theory. Each one described the universe differently. Some had open strings, some had closed loops, some required 26 dimensions, others only 10. They all seemed mathematically true, but they couldn't all be right. It looked like we had 5 different maps for the same territory, and none of them matched. Then, in 1995, at a conference at the University of Southern California, a physicist named Edward Witten walked onto the stage and started the second superstring revolution. Witten didn't just pick the best theory. He proved that the 5 different theories were actually just 5 different ways of looking at a single, much larger mathematical object. He called this master framework M theory. No one knows for sure what the M stands for: magic, mystery, membrane, or matrix. But the math was undeniable. To make the 5 theories fit together, Witten had to do something drastic. He added 1 more dimension. He took us from the 10 dimensions of string theory to the 11 dimensions of M theory. And in that 11th dimension, strings stopped being just 1-dimensional lines. They stretched out. A line stretched sideways becomes a sheet. A sheet stretched up becomes a volume. This gave birth to the concept of the brain, short for membrane. According to M theory, our entire observable universe, every star, every galaxy, every atom you see, is trapped on a single 3-dimensional D3 brain. We are living on a thin sheet of reality that is floating in a much larger, higher dimensional space called the bulk, or hyperspace. Think of a loaf of sliced bread. Our universe is just 1 slice. We can move left, right, up and down within the bread, but we cannot move out of the slice. We cannot enter the crust or the air around the loaf. We are stuck to the surface. This changes our definition of the universe. We used to think the universe was everything that existed. But in M theory, the universe is just an island. The bulk is the ocean. And just like an ocean, the bulk is vast, deep, and mostly empty. But oceans are rarely completely empty. So, the math says our reality is just a piece of paper floating in a dark room. But if we are just one sheet, what prevents another sheet, another universe, from floating right next to us? If the gap between the pages is small enough, could we reach out and touch it? If the bulk is real, if there is a massive, higher dimensional space right outside our universe, why can't we see it? Why can't we just turn our heads sideways and look into the fourth dimension? Why can't we see the other slices of bread in the loaf? The answer lies in the fundamental shape of matter itself. According to string theory, everything in the universe is made of tiny vibrating filaments of energy called strings. An electron is a string vibrating at one frequency. A quark is a string vibrating at another. But crucially, strings come in two shapes: loops, closed strings, and lines, open strings. This shape determines your freedom. The particles that make up your body, the protons, neutrons, and electrons, are all open strings. They look like tiny pieces of thread with two loose ends. And here is the rule that keeps us trapped. The ends of an open string must be attached to something. They cannot just float freely in the bulk. They have to be anchored to a D-brane. Think of the hairs on your arm. The hair can wave around, but the root is stuck in your skin. It cannot leave your body. In the same way, every atom of matter in our universe is physically rooted to our 3D brain. We are stuck to the surface of our reality like flies on flypaper. But the real tragedy is light. Photons, the particles that carry light and allow us to see, are also open strings. Their ends are pinned to our brain. This means that light can only travel along the surface of our universe. It cannot travel off it. You cannot shine a flashlight into the bulk. The beam will just travel in a straight line through our 3D space. It is physically impossible for a photon to leave our dimension. This is why the bulk is invisible to us. It isn't that there is nothing there, it is that we are blind. We are living on a 2D movie screen, trying to see the audience, but the light from the projector only exists on the screen. We are trapped in a prison of light. So, because light is shackled to our dimension, we are effectively locked in a windowless room. We cannot look outside. But if we can't look out, how do we know if someone or something is walking up to the house right now? So, we are locked in a room called the universe. We cannot see out because light is stuck to the walls. We cannot walk out because our atoms are glued to the floor. By all accounts, we should be completely isolated from whatever is happening in the higher dimensions. But there is one thing that can escape. One force that refuses to be contained. Gravity. According to string theory, the particle that carries the force of gravity, the graviton, is fundamentally different from every other particle in existence. While electrons and photons are open strings with loose ends that must stick to the brain, a graviton is a closed string. It is a perfect loop. It has no ends. This sounds like a minor geometric detail, but it changes the rules of the prison entirely. Because a loop has no sticky ends, it cannot be anchored to our 3D brain. It is chemically impossible for the universe to hold onto it. This means that gravity is free to float off the surface of our world. It can drift into the bulk. It can vanish into the fifth dimension. This explains one of the deepest, most frustrating mysteries in physics, the hierarchy problem. Why is gravity so incredibly weak? Think about a simple fridge magnet. That tiny piece of metal can pick up a paperclip against the gravitational pull of the entire Earth. The planet is massive, yet a magnet the size of a coin beats it effortlessly. Gravity is 10 to the power of 36 times weaker than electromagnetism. It makes no sense, unless gravity isn't actually weak. String theory suggests that gravity is just as strong as the other forces, but we only feel a tiny fraction of it because most of it is leaking out of the universe. It is diluting into the extra dimensions like sound passing through a thin wall. But here is the terrifying implication of a leaking wall. It works both ways. If our gravity can leak out into the bulk, then the gravity from the bulk can leak into us. We might not be able to see the neighboring universe, but if it has mass, we should be able to feel its weight. So, the walls of our reality are porous. We are losing energy to the outside, and that means something from the outside can push back. But if a massive object in a parallel universe moved close enough to our wall, would we just feel a vague heaviness? Or would we feel a specific, localized crush? If there is a bulk, and if gravity leaks into it, how far away is the other side? In science fiction, parallel universes are usually depicted as distant realities, separated by impossible gulfs of space and time. We imagine them as bubbles floating billions of light years apart in a cosmic foam. But in 1999, physicists Lisa Randall and Raman Sundram published a pair of groundbreaking papers, known as RS1 and RS2, that destroyed this comfortable idea of distance. They built a mathematical model of a warped 5-dimensional geometry that describes our universe not as a lonely bubble, but as a wall in a narrow room. According to their equations, the extra dimension, the bulk, isn't vast. It is incredibly, terrifyingly thin. The distance between our D-brane and the neighboring one could be as small as 1 millimeter. Even at the upper limit of the theory, the gap might be as large as 1 millimeter. Think about that scale. 1 millimeter. That is the thickness of a dime. That is less than the width of your skin. This implies that the multiverse is not a faraway place. It is spatially superimposed right on top of you. There could be an entire other universe, with its own stars, its own planets, and its own laws of physics, hovering literally less than an inch from your face right now. The reason you can't see it or touch it is that you are trapped in 3D space. You're like a character in a video game who can move left, right, forward and backward, but cannot move out of the screen towards the player. The player is inches away, but to the character, the player exists in a direction that mathematically does not exist. But while photons cannot cross that millimeter gap, we establish that gravity can. Gravity is the only force that can reach across the aisle. This means that if a massive object in that neighboring universe, a planet or a black hole, passed close to our brain in the 5th dimension, we would feel it. We wouldn't see anything. To us, it would look like invisible gravity appearing out of nowhere. So the math suggests that the other is not distant. It is intimate. It is hovering right next to your retina. But if another reality is floating just a millimeter away, do you really think it's just staying there, static and safe? Or is it moving closer? In the quantum world, empty space is never truly empty. It is seething with virtual particles popping in and out of existence. This creates a pressure. In 1948, the physicist Hendrik Casimir predicted a bizarre effect. If you take 2 uncharged metal plates and place them extremely close together in a vacuum, they will mysteriously push towards each other. Why? Because the gap between the plates is so small that only small quantum waves can fit inside it. But outside the plates, waves of all sizes can exist. This creates a pressure difference. There are more particles pushing from the outside in than from the inside out. The result is a net force of attraction. The plates are crushed together by the vacuum itself. This effect, the Casimir force, has been proven in the lab. We have measured it. Nanotechnology engineers have to account for it because it makes tiny machine parts stick together. But here is the problem for cosmology. Brains act exactly like those metal plates. If our universe is a membrane floating in the bulk, and there is another membrane floating parallel to it just a millimeter away, the quantum fluctuations in the 5th dimension will create a massive Casimir force between entire universes. This means the system is fundamentally unstable. 2 parallel universes cannot just float peacefully forever. The vacuum pressure of the bulk will inevitably push them together. It acts like a cosmic zipper, closing the gap. The closer they get, the stronger the force becomes, and the faster they accelerate. We are not just drifting, We are being magnetically pulled toward a collision. The dark flow we discussed earlier might not be us moving through space. It might be our entire brain bending under the pressure of an approaching wall. So, the laws of quantum mechanics demand that parallel worlds eventually touch. The distance is shrinking every second. But what happens to the delicate structure of our matter, to your atoms, when two infinite sheets of reality slam into each other? In 1956, physics broke. Until that moment, scientists believed in a fundamental rule called parity conservation. It essentially meant that the laws of physics are symmetrical. Nature shouldn't care about left or right. If you watch a physical process in a mirror, it should look just as natural as the real thing. Gravity pulls down, not left. Electromagnetism works the same way if you swap positive for negative. But two young physicists, Tsung-Dao Lee and Chen-Ning Yang, noticed a crack in the mirror. They studied the decay of cobalt-60 atoms and found something impossible. The subatomic particles, electrons, preferred to fly out in one specific direction. They were left-handed. This was a catastrophe. It meant the universe was biased. It meant that, at a fundamental level, nature distinguishes between left and right. To save the symmetry of the universe, physicists, later including Kobzarev, Okun, and Pomeranchuk, proposed a radical solution. They suggested that for every particle we know, every proton, every neutron, every electron, there must exist a corresponding mirror particle to balance the equation. If our matter is left-handed, there must be a right-handed version of matter out there to restore the balance. This creates the hypothesis of mirror matter. Here is the terrifying part. Mirror matter is not antimatter. Antimatter explodes when it touches you. Mirror matter ignores you completely. Mirror atoms have their own version of the electromagnetic force. They have mirror photons. This means that mirror matter can form stars that shine with mirror light. But because mirror photons do not interact with our retinas or our cameras, that light is utterly invisible to us. A mirror star could be blazing in the sky right now, bathing the Earth in high-intensity radiation, and you would see pitch blackness. Mirror light passes through your roof, your skin, and the planet itself as if it were nothing. The only way these two worlds interact is through gravity. Gravity is the universal language. If a mirror planet drifted into our solar system, we wouldn't see it blocking the stars. We would only feel its mass throwing our orbit into chaos. So, the math demands that a second, invisible periodic table exists to balance our own. But if invisible light is shining through your window right now, can we be sure that invisible life isn't standing in the room with you? For decades, astronomers have comforted themselves with the idea that dark matter, whatever it is boring. The standard model assumes that dark matter is a collisionless halo. Imagine a giant, fluffy cloud of ghost particles surrounding the Milky Way. It doesn't clump. It doesn't form planets. It just hangs there, providing the extra gravity needed to hold our galaxy together. But in 2014, Harvard theoretical physicist Lisa Randall asked a simple, disturbing question. Why should dark matter be simple? Visible matter is complex. It forms atoms, molecules, rocks, and people. It does this because it can radiate heat and cool down. Randall proposed a new model called double-disk dark matter. She argued that a fraction of the dark sector creates its own dark electromagnetism. This allows it to shed energy, cool down, and collapse into dense structures. If the dark matter can cool, it doesn't stay a fluffy cloud. It flattens into a disk. Randall's calculations suggest that embedded directly inside our own Milky Way galaxy, there is a second, invisible dark disk. It rotates in the same plane as our stars. It has the same spiral structure. This changes the game entirely. If dark matter can form a disk, it can form dark atoms. And if it can form atoms, it can form dark chemistry. We are talking about a shadow galaxy superimposed perfectly on top of our own. Because this disk is dense, it implies that dark matter isn't just drifting as a gas. It creates solar systems. It creates compact objects. There could be dark stars, burning with invisible fusion, orbited by dark planets made of invisible rock. And because the dark disk is thinner and denser than the visible one, these shadow objects are constantly passing through our own star systems. We are not alone in our galaxy. We are sharing our living room with a ghost that is just as complex, just as structured, and just as heavy as we are. So if the galaxy contains a second invisible disk of planets spinning right alongside us, what happens when our paths cross? Can a dark planet collide with the Earth? And would we even know what hit us before the gravity tore the ground apart? If you accept the existence of a dark disk, a complex cooling structure of mirror matter, you have to accept the inevitable conclusion of complexity. In our visible universe, the jump from physics to chemistry is just a matter of cooling down. Protons catch electrons, form atoms, and bond into molecules. And once you have chemistry, once you have carbon chains and complex polymers, the jump to biology is just a matter of time and thermodynamics. This leads to the concept of the shadow biosphere. Astrobiologists at NASA and physicists like Paul Davies have seriously proposed that life on Earth might not be limited to the life we know. We assume that all life is built from our periodic table. But if the dark sector has its own dark protons and dark electrons, it must have its own dark periodic table. This implies that right here, occupying the exact same volume of space as the Earth, there could be a shadow Earth. It would be a planet made of dark matter, governed by dark chemistry. Here is the mind-bending part. Because dark atoms do not interact with our light, photons, they do not have electromagnetic fields that push against ours. Solidity is an illusion. The reason you don't fall through the floor is that the electrons in your boots repel the electrons in the wood via electromagnetism. But dark matter has no such repulsion against us. This means a shadow rock, a shadow tree, or a shadow being has no physical barrier to us. They would be completely intangible. A complex dark organism could walk straight through a concrete wall. It could walk straight through your body. Its atoms would glide between your nuclei without ever colliding. To them, we are the ghosts. To us, they simply don't exist. We could be living in a crowded room. There could be an entire ecosystem, predators, prey, bacteria, civilizations, superimposed right on top of our own. We occupy the same coordinates, but we are tuned to different frequencies of reality. So, physics says that two solid objects can occupy the same space if they don't share forces. But if a shadow entity is standing in the middle of your living room right now, staring at you, would you ever know? Or would you just feel a cold draft as its atoms pass through your spine? But there is one exception to this ghost rule. We said that dark matter doesn't touch us. That is true for electromagnetism. But it is not true for gravity. Mass is mass. It doesn't matter if the mass is made of light protons or dark protons. It warps space-time exactly the same way. If a shadow object is dense enough, you will feel it. Imagine a shadow planet passing through our solar system. We wouldn't see it block the sun. But suddenly, the tides on Earth would go haywire. Orbits would shift. If a smaller object, say a shadow asteroid or a dense biological form, passed through your house, the local gravity would spike. You would feel a sudden, inexplicable heaviness. This provides a terrifying physical explanation for phenomena we usually dismiss as hallucinations or sleep paralysis. In that state, people report a distinct feeling of a heavy weight pressing down on their chest. They report a presence in the room that they cannot see. They feel like they are being crushed by an invisible force. To a neurologist, this is a brain glitch. But to a physicist studying the dark sector, this is exactly what a gravitational collision would feel like. If a being made of mirror matter sat on your chest, its atoms would pass through your ribs, but its gravity would not. Its mass would pull on your lungs. It would compress your heart. You would feel the physical weight of a creature that your eyes literally cannot register. We assume that just because we can't see them, they can't hurt us. But gravity is a force that crushes. If the density of the shadow biosphere is high enough, we are constantly walking through a minefield of invisible gravitational wells. So, the only way we can sense them is through weight. But if you woke up tonight unable to move, pinned to your mattress by an invisible pressure, would you assume it was a dream? Or would you realize that something from the shadow sector has decided to lie down right where you were sleeping? On June 30th, 1908, the sky above Siberia split open. An explosion estimated at 50 megatons, roughly 3,000 times powerful than the atomic bomb dropped on Hiroshima, flattened 2,000 square kilometers of forest. Trees were snapped like matchsticks. The shockwave went around the world twice, but when expeditions finally reached the site, they found something impossible. There was no crater. There were no fragments of meteorite. There was no trace of the object that had struck the Earth with the force of a nuclear weapon. For a century, scientists have tried to explain this away. They said it was an ice comet that evaporated before impact. They said it was a rocky asteroid that exploded in the air. But even airbursts leave chemical traces or microscopic dust. Tunguska left nothing. This leads us to one of the most exotic hypotheses in modern physics: the mirror matter impactor. Physicists Robert Foote and Zurab Siligadze have proposed that the object wasn't a normal rock. It was a mirror asteroid. Here is why the physics fits perfectly. If a rock made of mirror matter enters our atmosphere, it does not interact with the air molecules. It feels no friction. It generates no heat. There is no glowing trail in the sky. To a human observer, the asteroid is completely invisible. It falls silently through the clouds like a ghost. It only releases its energy when it physically strikes the dense crust of the Earth, or when the internal pressure of the mirror matter becomes unstable deep underground. If this hypothesis is true, it means the Tunguska event wasn't an explosion from above. It was a release of energy from an object passing through the planet. It implies that our solar system is filled with invisible debris. A mirror asteroid could be on a collision course with New York City right now. Our telescopes wouldn't see it. Our radar wouldn't detect it. We wouldn't know it was coming until the city simply ceased to exist. So, a rock weighing millions of tons could pass through the atmosphere without moving a single molecule of air, only to detonate on the ground. But if solid objects can pass through us like light, what happens when we try to catch the wind of this invisible world? Deep beneath the Gran Sasso mountain in Italy, shielded from cosmic radiation by 1,400 meters of solid rock, lies the Dama/Libra experiment. For over 20 years, this machine has been looking for one thing: the touch of dark matter. Most detectors try to find a single particle hitting a sensor, but Dama looked for something else. They looked for a seasonal weather pattern. Here is the logic. Our galaxy is surrounded by a halo of dark matter. It is a stationary cloud. Our solar system is moving through this cloud at 220 kilometers per second. This creates a dark matter wind blowing against us, but the Earth also orbits the Sun at 30 kilometers per second. In June, the Earth is moving in the same direction as the Sun, driving straight into the wind. The speed adds up. 220 plus 30. The wind is faster. In December, the Earth is moving backward, away from the wind. The speed subtracts. 220 minus 30. The wind is slower. If a dark matter is real, the detector should register more hits in June and fewer in December. It should breathe. And for 2 decades, that is exactly what the data has shown. The Dama/Libra signal modulates perfectly with the seasons. The statistical significance is 9 sigma. In physics, 5 sigma is a discovery. 9 sigma is a certainty. The probability of this being a fluke is virtually non-existent. This experiment proves that we are not moving through empty space. We are flying through a storm. Right now, as you sit there, you are being blasted by a wind of invisible particles moving at nearly 1 million miles per hour. Millions of these particles are passing through your thumb every second. They are passing through your brain. We assume they don't interact with us, but the Dharma detector flashes because occasionally they do hit. So, we're immersed in a high-speed wind of alien matter that fluctuates with the seasons. We know it passes through our bodies. But if these particles have mass, and they are hitting your DNA millions of times a day, are they leaving a mark? In 1957, a graduate student at Princeton named Hugh Everett III looked at the fundamental equation of quantum mechanics, the Schrödinger equation, and noticed something that terrified him. The equation describes particles as waves of probability. According to the standard dogma, the Copenhagen interpretation, when you measure a particle, the wave collapses. It chooses one state. The coin spins, and then it stops on heads. The tails possibility simply vanishes from existence. But Everett looked at the math, and he realized that the equation never actually collapses. The math does not have a stop function. It just keeps evolving. Everett proposed a radical correction. The wave function never collapses. Instead, the universe splits. When you measure the particle, the universe physically bifurcates into two separate, equally real timelines. In one, the coin is heads. In the other, the coin is tails. You, the observer, also split. There is a version of you who sees heads, and a version of you who sees tails. Both of you think you are the only one. Both of you are real. This is the many worlds interpretation. It implies that our reality is not a single timeline. It is an infinitely branching tree known as Hilbert space. Every time a subatomic particle interacts with another, which happens trillions of times a second in your body, the universe fractures. This means that right now, there are infinite variations of you branching off from this moment. In one branch, you stopped reading this sentence. In another, you spilled your coffee. In another, a cosmic ray struck your DNA and started a cancer. These are not hypothetical what-if scenarios. In MWI, they are physical places. They have mass. They have energy. The you in those branches is just as conscious as the you sitting here. The only difference is that you can't see them because the branches have decohered. They have vibrated out of sync with each other. So, physics says that every possible version of your life exists simultaneously in a vast, invisible stack. But if there are billions of physical copies of you created every second, what makes you think that the version reading this text is the original? What if you are just the throwaway copy? For decades, we comforted ourselves with the idea that even if these other worlds exist, they are completely separated from us. Once the split happens, the door is closed. The branches never touch. This is called decoherence. It is the wall that keeps our reality stable. But recent experiments by physicist Yakir Aharonov have found a crack in the wall. He developed a technique called weak measurement. Instead of hitting a particle hard to force a result, you touch it gently. You barely look at it. This allows you to see the quantum state before the universe fully splits. And what he found is terrifying. The branches interfere. Before two realities completely separate, they rub against each other. A particle in our world can change its trajectory because it bumped into its own ghost from a neighboring world. Think about two swimmers swimming in parallel lanes. They don't touch, but the waves from one swimmer push against the other. The ghost swimmer, the version of the particle in the other branch, creates a physical force that nudges the real swimmer, our particle. This phenomenon is called interaction-free measurement. It proves that non-existent objects can exert force on existing ones. The alternate timeline where the particle went left is pushing the particle that went right. Now, apply this to the most complex quantum machine in the known universe, your brain. Neurons fire based on ion channels opening and closing, a process governed by quantum mechanics. If weak measurement is true, then the electrical signals in your brain are subject to interference from your alternate selves. The version of you in the branch next door, the one who made a slightly different choice, might be chemically bumping into your neural pathways right now. So, physics suggests that your thoughts are not entirely private. They are being jostled by the thoughts of the versions of you that didn't make it. But if a sudden, intrusive thought pops into your head, a thought that feels alien, is it really yours? Or is it a signal bleeding through from a timeline where you are a very different person? For years, the internet has been obsessed with the Mandela effect, the phenomenon where large groups of people distinctly remember historical facts differently than recorded history. They remember Nelson Mandela dying in prison in the 1980s. They remember the Berenstein Bears instead of Berenstain. Psychologists call this false memory. They say the human brain is glitchy. It reconstructs the past imperfectly. But in the physics of the multiverse, this glitch might not be in your head. It might be in the timeline itself. If our reality is a brain floating in a bulk, and if there are infinite other brains floating nearby, then collisions are inevitable. We usually imagine a collision as a violent, fiery event. But what if the membranes just brush against each other? What if two very similar timelines briefly merge and then separate again? In information theory, this is called a data overwrite. Imagine two hard drives copying files to each other. If timeline A, where Mandela died, touches timeline B, where Mandela lived, the information structures might get entangled. When they separate, the physical reality of timeline B might overwrite the physical reality of timeline A. The books in the library change, the letters on the cereal box change, the history books change, but here is the horror. Your brain is a quantum system. Neural networks rely on quantum effects in microtubules. It is possible that while the macroscopic physical record, the book, gets overwritten by the collision, the microscopic quantum state of your memory, the neuron, retains the old data. You are left holding a memory of a world that physically no longer exists. This implies that your consciousness is not hallucinating. It is a refugee. It is holding on to a piece of information from a timeline that was deleted or merged into this one. The dissonance you feel isn't confusion, it is the friction of a mind from world A trying to operate in world B. So, if you remember something that history says never happened, maybe you aren't crazy. Maybe you were just the only one who didn't get the software update. But if your past can be rewritten while you sleep, how much of your life story actually happened in this universe? This brings us to the darkest, most personal implication of the many worlds interpretation. It is a thought experiment that has haunted physicists since the 1980s. It is called quantum suicide, or more terrifyingly, quantum immortality. The logic is brutally simple. Consciousness requires a physical substrate, a brain, to exist. You cannot experience nothingness. You cannot experience being dead. Therefore, from your own first-person perspective, the only timeline you can ever inhabit is the one where you are alive. Imagine a game of Russian roulette. You put one bullet in a revolver, spin the cylinder, put it to your head, and pull the trigger. In a single universe model, you have a 1 in 6 chance of dying. But in the many worlds model, the act of pulling the trigger is a quantum event. The universe splits. In 5 branches, the hammer clicks on an empty chamber. You live. In one branch, the gun fires. You die. Here is the trap. The you in the death branch ceases to exist instantly. The screen goes black. But the you in the survival branches hears the click. You are still there. From your subjective perspective, the gun simply refused to fire. Now imagine you pull the trigger again, and again, and again 50 times. In the vast majority of universes, you are dead. Your family is burying you. But in that one, thin, impossibly unlikely sliver of probability where the gun jammed 50 times in a row, you are still observing. You are trapped in the survival timeline. This theory suggests that you, the observer behind your eyes, can never die. You will survive every car crash. You will survive every terminal disease. You will survive old age, perhaps hooked to machines, or perhaps as a freak biological anomaly. As everyone you love dies in the probabilistic branches around you, you are forced to continue in the increasingly lonely, increasingly strange branch, where you simply keep going. So, think back to a moment in your life where you narrowly avoided death. A car that missed you by an inch. A sickness you shouldn't have recovered from. Are you sure you survived? Or did you die in the main timeline, and the consciousness reading this text right now is just the backup copy that loaded in the next branch? In 2006, NASA launched a balloon-borne instrument called ARCADE, Absolute Radiometer for Cosmology, Astrophysics, and Diffuse Emission, to the edge of the atmosphere. Its mission was boring. To listen to the faint, static hiss of the early universe, the radio waves left over from the first stars. Scientists expected to hear a quiet whisper. They had calculated exactly how loud the universe should be, based on the number of galaxies and the intensity of the Big Bang. But when they turned the microphone on, they didn't hear a whisper. They heard a scream. The instrument detected a radio signal that was 6 times louder than predicted. At first, the team assumed the instrument was broken. They checked for interference from Earth, from the Sun, from the galaxy itself. They subtracted every known source of radio waves in the cosmos, every supernova, every gas cloud, every black hole. But after filtering out everything that exists, the signal remained. It was a booming, omnipresent wall of noise coming from every direction at once. They called it the space roar. This is not a subtle anomaly. It is like expecting to hear a pin drop in a library and hearing a jet engine instead. The signal is so powerful that it drowns out the radiation from the actual stars. Here is the problem. There aren't enough radio sources in our universe to create this noise. Even if you packed every inch of the sky with galaxies, they wouldn't be loud enough to generate the signal ARCADE found. The math says the source cannot be inside the room. This leaves only one terrifying option. The walls of the room are vibrating. In the context of brain cosmology, this roar is exactly what you would expect to hear if our universe were rubbing against another one. Think of 2 balloons pressing against each other. As they slide, the friction creates a squeak. But when the balloons are the size of universes, that squeak becomes a roar of radio energy that floods the entire cosmos. We are listening to the friction of the 5th dimension. The background noise of our reality isn't static. It is the grinding of our brain against a neighbor that is getting too close for comfort. So, if the static on your radio isn't just noise, but the sound of our reality scraping against something else, what happens when the grinding stops and the snapping begins? If the noise is getting louder, does that mean the other wall is leaning in? While NASA hears the roar in space, people on the ground are starting to hear something else. Since the 1970s, in places like Bristol, UK, Taos, New Mexico, and Windsor, Canada, thousands of people have reported a maddening, persistent, low-frequency sound. They call it the hum. It sounds like a diesel truck idling down the street, or a massive generator buried deep underground. It is a physical vibration that rattles windows and causes nausea, headaches, and nosebleeds. But when acoustic engineers arrive with microphones to find the source, they find nothing. There is no truck. There is no factory. The sound doesn't fade when you put on earplugs. It doesn't stop when you go into a soundproof room. It seems to bypass the ear and vibrate directly in the skull. Doctors dismiss it as tinnitus, but tinnitus is a high-pitched ring, not a low-frequency rumble. And tinnitus doesn't strike thousands of people in specific geographic clusters at the exact same time. Cosmologists observing the interactions of brains suggest a darker origin. If 2 membrane universes are drifting closer together, the gravitational tension between them will fluctuate. Before they touch, they interact via gravitational waves. These are ripples in the fabric of space-time itself. If a massive gravitational wave from the approaching brain passes through the Earth, It would compress and stretch the planet slightly. It would vibrate the crust. To a human being, a vibration of the Earth's crust at a specific frequency, around 10 Hz, wouldn't feel like an earthquake. It would feel like a sound. It would be an infrasonic resonance felt in the bones rather than heard in the ears. The hum might not be industrial noise. It might be the creaking of the Earth as it is squeezed by the gravity of an approaching universe. It is the sound of the pressure building up before the pop. So, the sensors in space hear a roar, and the people on Earth feel a rumble. The pressure is rising from both sides. But if this sound is the result of friction between worlds, and the friction is getting worse, can you hear it right now in the silence of your room? In 2001, at the Institute for Advanced Study in Princeton, physicists Paul Steinhardt and Neil Turok proposed a model that horrified the scientific community because it took away our beginning. For decades, we have been told the story of the Big Bang. 13.8 billion years ago, the universe exploded out of a singularity, a point of infinite density, and created time and space from nothing. It was a one-time event, a miracle of physics. But Steinhardt and Turok looked at the math of string theory and realized that the Big Bang looked suspiciously like a collision. They developed the ekpyrotic model, from the Greek for conflagration or fire. In this model, our universe is a D-brane, and there is another empty shadow brane floating parallel to us in the bulk. Every few trillion years, these two massive sheets of reality drift together. When they touch, the kinetic energy of the impact is converted instantly into heat and radiation. To an observer inside the brane, this moment looks exactly like a Big Bang. The universe fills with fire. Matter is vaporized. Space expands rapidly from the shockwave. This means that the Big Bang was not the beginning of time. It was just the latest clap of thunder in an eternal storm. It implies that our universe is stuck in a cycle of destruction and rebirth. Bang, expansion, cooling, attraction, crash, bang. We are currently living in the cooling phase. The plates have bounced off each other and are drifting apart. Life has had a chance to evolve because the fire has died down. But gravity is a relentless spring. It is already slowing down the drift. It is already pulling the plates back together. So, if our entire history is just the cooling period between two crashes, that means the peace cannot last forever. We are living in a pause. But if the cycle is automatic, does that mean the next collision is already scheduled? This brings us to the biggest mystery in modern cosmology: dark energy. In the late 1990s, we discovered that the expansion of the universe isn't slowing down as gravity pulls things together. It is speeding up. Galaxies are flying away from each other faster and faster every day. Physicists invented dark energy as a placeholder name for this mysterious, invisible force that is pushing the cosmos apart. But in the ekpyrotic model, dark energy isn't a push, it is a pull. Think about two magnets floating in space. As they get closer, the magnetic force gets stronger, and they accelerate towards each other. Steinhardt and Turok argue that the acceleration we see in the universe today is actually the gravitational attraction between our brane and the neighboring shadow brane. The reason the galaxies seem to be flying apart is that the entire dimension is being stretched as it falls toward the collision point. We are not expanding into a void. We are free falling toward a wall. The fact that the expansion is accelerating is the smoking gun. It means the gap is closing. The closer we get to the other brane, the faster we move. We are in the final stage of the approach. The dark energy value is just a measure of how close the impact is. So, the universe is pressing the gas pedal. We are racing towards something at an exponential speed. But if the speed is increasing, does that mean the impact isn't billions of years away, but potentially much closer? If the collision of entire universes sounds too abstract, there is a much more immediate way for physics to end you. It comes from the stability of the vacuum itself. In quantum field theory, vacuum doesn't mean empty. It means the lowest possible energy state of a field. Imagine a ball sitting at the bottom of a valley. If you kick it, it rolls back down. It is stable. This is a true vacuum. But imagine a ball stuck in a small dip halfway up a mountain. It looks stable. It stays put for now. But if you give it a hard enough kick, it will roll over the edge and crash all the way down to the real bottom. This is a false vacuum. For decades, we didn't know which kind of vacuum we lived in. Then, in 2012, at the Large Hadron Collider, we found the Higgs boson. The Higgs is the particle that gives mass to everything else. Its mass was measured at approximately 125 gigaelectronvolts, GeV. This specific number is the worst possible news for the stability of the universe. If the Higgs were lighter, the universe would be stable. If it were heavier, it would be unstable and would have collapsed already. But at 125 gigaelectronvolts, we are in the Goldilocks zone of the apocalypse. We are metastable. We are the ball stuck in the dip halfway up the mountain. This implies that our vacuum is not the true bottom. There is a lower energy state waiting below us. All it takes is a kick, a high energy quantum event, to knock the Higgs field over the edge. If this happens, a bubble of true vacuum will nucleate. Inside this bubble, the laws of physics are rewritten. The constants of nature change. Chemistry becomes impossible. Atoms cannot hold together. This bubble would expand at the speed of light, consuming everything in its path. So, the ground beneath your feet is not solid. It is a trapdoor held shut by a rusty latch. At any moment, in any corner of the universe, a quantum fluctuation could pop the latch. And because the bubble expands at light speed, you would never see it coming. 1 second you're reading this text, and the next second, your atoms simply cease to exist. Here is the cruelest joke in physics. The same law that lets us see the stars also blinds us to their destruction. We rely on light to warn us of danger. If a lion is running at you, you see it before it bites. If a hurricane is coming, you see the clouds. We assume that if the end of the world were approaching, if a bubble of true vacuum were expanding, or a neighboring brain were crashing down, we would see it coming. We expect the sky to darken. We expect the stars to wink out one by one. But physics forbids this warning. The shock wave from a vacuum decay or brain collision propagates with a speed exactly equal to c minus the speed of light. This is the cosmic speed limit for information. No signal, no image, no radio wave can travel faster than the wave of destruction itself. The news of the apocalypse arrives at the exact same instant as the apocalypse. Think about what that means for your experience of the end. You could be looking directly at the point in the sky where the bubble originated 1 billion years ago. To your eyes, that patch of sky looks perfectly normal. You see stars shining as they did in the past. You see galaxies spinning. The light from those stars is hitting your retina at the same moment the wall of energy hits your face. There is no before. There is no during. There is only after. You would never feel pain. The nerve impulses traveling from your skin to your brain move at about 100 meters per second. That is agonizingly slow compared to the speed of light. The wall of new physics would dismantle your neurons, your atoms, and your consciousness before the electrical signal even reached your spine. You wouldn't even know you had died. One moment, you are drinking coffee, worrying about an email, or watching this video. In the very next nanosecond, without a flash, without a sound, you simply cease to be. The continuity of your consciousness is snipped like a film reel. So, the universe guarantees that the end will be a surprise. But if the wall hits us faster than the speed of thought, does it even count as death? Or is it just a sudden, painless switch to black? But death is personal. The universe doesn't care about your body. The universe cares about information. In standard physics, there is a rule called unitarity. It says that information is never lost. If you burn a book, the information is scrambled into ash and smoke, but theoretically you could reconstruct it. but a phase transition, like the collision of branes or the decay of the vacuum, breaks this rule. It is the ultimate Format C command. When the wall hits, it doesn't just burn matter, it rewrites the laws of physics that allow matter to exist. The binding energy that holds quarks together is released. The electromagnetic force that holds your memories in your brain is reset to zero. Matter returns to quark-gluon plasma. This is the primal soup. It has no structure. It has no history. In this state, a carbon atom that was once part of Shakespeare is identical to a carbon atom that was part of a dinosaur. The distinction is gone. This means that everything humanity has ever built, the pyramids, the internet, the Apollo moon landing, the song you are listening to, is instantly converted into random thermal noise. There will be no ruins left for the next civilization to find. There will be no Voyager probe drifting in the dark to prove we were here. The hard drive is not just wiped, it is melted down and cast into a new shape. In the ekpyrotic model, this destruction is actually a cleaning process. The collision wipes the slate clean so the cycle can start again. The universe is not a museum, it is a recycling plant. We are just the temporary patterns in the dust before the next wind blows. So, if this has happened trillions of times before, countless civilizations have likely risen, looked at the stars, and been erased just like us. But if we are destined to be forgotten, what is the point of the time we have left? We have spent the last 20 minutes tearing reality apart. We looked at the cold spot and found a scar from a collision. We looked at the dark flow and found that we are drifting in a cosmic river. We listened to the space roar and felt the pressure of invisible walls. The data from Planck, from Kashlinsky, from Dharma/Libera, it all points to one conclusion. The system is unstable, and we are not in control. Logically, this should terrify you. It makes your mortgage, your job, and your social status look absurdly small. But if you flip the perspective, this is the most liberating news you will ever hear. We spend our lives stressed because we think we are the main characters. We think the weight of the world is on our shoulders. We worry about making the wrong choice. But physics tells us that we are just passengers on a rock, falling through a gravity well, inside a bubble, floating in a bulk that is governed by forces so massive they make our entire history look like a rounding error. You cannot stop the branes from colliding. You cannot steer the galaxy out of the dark flow. You cannot patch the false vacuum, and that means you are free. If the universe is a giant, uncontrollable machine destined to reboot, then your only job is to enjoy the ride. The scale of these problems is so huge that it cancels out your personal anxieties. Did you embarrass yourself at a party? Who cares? The universe is colliding with another dimension. Are you worried about your bank account? It doesn't matter. The vacuum might decay tomorrow. This creates a cosmic nihilism that actually feels like relief. It gives you permission to stop taking everything so seriously. It gives you permission to just be. We are the lucky chemical scum that woke up for a brief nanosecond in the middle of the fireworks show. We got to see the stars. We got to feel the sun. We got to ask the question, why? That is a miracle. We are walking a tightrope over a bottomless pit, but the view is spectacular. So, stop looking down at the abyss. Look up, grab a coffee, hug someone you love, and appreciate the fact that right now, in this improbably stable second, your atoms are holding together long enough to feel something. If this journey through the cracks in our reality shifted your perspective, hit the like button. It helps the signal reach other observers before the simulation resets. I want to know what you think in the comments. Does the idea of a dark flow pulling us scare you, or does it make you feel part of something bigger? Let's discuss it down there. And if you want to keep exploring the terrifying beauty of the cosmos with me, if you want to know what else is hiding in the dark, make sure to subscribe and ring the bell. We have a lot more blueprints to examine. Thank you for watching. And remember, The universe may be broken, but you are still here. Enjoy it.